the grating. So the grating is very simple. You use diffraction. You exploit the diffraction. So you have that your mode is moving into the waveguide, and then it encounter an optical grating, so a diffraction grating. And therefore, you have different order of diffraction. And what you do is that you simply engineer your grating in such a way that the first order diffracted mode is exactly directed out of the chip. And so in this way, you can quite easily get your light that is coming from the waveguide, and it is diffracted out into the single mode fiber here, or you can get that your light is coming from the single mode fiber and then is diffracted into your waveguide. Simple. And it is work quite well. So you can get less than 1 dB of coupling losses. So you lose 10% of light in your coupling. And then the other advantage is the fact that if you use grating, so the package is also very simple, very easy. So here is an example of one of those package wafers that we have. So this is silicon. And here you have a fiber array, so a piece of glass where you have many fibers. And those fibers are glued onto the circuit. And the reason why you can glue quite efficiently is the fact that now the grating has overall dimension that's similar to the one of the fibers. So 50 micron in size. And so it's very easy to place your fiber there and couple and get the light that is traveling into your circuit. Then the last topic. So since it's transparent, you have a problem with silicon. A disadvantage is the fact that since it is transparent, you cannot absorb. And so, but you need to have absorption of light because you need to detect those photons in order to convert the photon beam into an electrical signal that then you can process. And therefore, so you need to solve this issue. And this issue is associated to the fact that silicon band gap is at about 1.1 micron. And therefore, it's very good in absorbing light in the visible. And this is the reason why optical sensor, photovoltaic cell are made by using silicon. But it's completely transparent in the blind in the region where you have your light. And this is the reason why you use silicon for guiding light. And therefore, the only chance that the only possibility that we have is that to use an hybrid approach. So put on top of silicon something that is not silicon. What we can do is that we can put germanium, or we can put indium gallium arsenide or indium gallium arsenide and phosphide. You know what are the problems by doing that? What is the problem if you want to put germanium on top of silicon? Epitaxial growth of germanium on top of silicon. What is the problem? Exactly. Strain. So they do have a different lattice parameter. And therefore, you put your germanium on top of silicon and it's getting strained. And so the strain, so the stress at the interface is released by making defects, dislocation defects. And so you can put germanium, but you get a very poor germanium on top of silicon. And so you do not get any good photodiode. And therefore, people have developed a technology, because nowadays so you can have this germanium photodiode on silicon, a technology by which what they do is that they deposit a first layer of low temperature germanium that is essentially used in order to localize the dislocation at this interface. And then on top of which they put a very good quality germanium. And so in this way, so they are able to put germanium on top of silicon. And indeed, so this is an example of one of those germanium photodetectors that have been implemented in silicon. So this is a work by my friend Laurent Vivien in Paris. So here you have your waveguide. Here you have your piece of germanium. So the light is absorbed by the germanium. And then you can demonstrate that you can operate this germanium photodiode at very high frequency that is in excess of 50 gigahertz. So you can use those detectors in optical telecommunication quite easily. And then you have also a problem with silicon, that is the fact that silicon has a no electro-optic effect. But I think that is good to stop here a few minutes, and then we can restart.
So we'll have a 10 minutes break, and then again we'll start after 10 minutes. Okay, thank you, sir. Coconut water, will you like to have?
Right now?
Yes, it will hydrate you.
Okay. Yeah, I need to turn off. I need to go.
interact with him during the break, okay? One by one you take the chance. All the students who are come here. You think, हाँ सुने आए और चले गए इससे class में understood? Class की जो teacher है that is there only for forever. नहीं है तो बात भी कर सकते हैं, but this has to be leave after a week, right? And if he has come all the way from there to here, at least 10 minutes time, every one of you has come and listened. And this is works. Everybody. UG, PG, everyone. Answer, what is anyone else? I will individually come and ask what is to ask him. Okay. So one by one for 5 minutes also. सबको मैं पूछने हूँ. Okay. This is the purpose that you are studying here. You are studying a course. You have a foreign expert who has come to deliver. 10 years back, I met him in some course like this. Right? He told me, and then he is coming. So like this is how the networking goes. So पहले होता था कि पानी के पास रहना पड़ता था कॉलेज. Now पानी के कॉलेज के पास आ रहा है. You are the one who is thirsty for knowledge. You have to be studying. Right? In the summer, he has come and this weather is very good. You know, in this weather is very good. It's very hot. Okay? You students, what is available? यहाँ आए हैं तो you have to interact with them. Every one of them. लंच करके जाना अभी ये डिजिटल So now we'll welcome back Professor Pavesi. We'll start with the second session of the day. Okay.
So then I need to turn on the microphone, and then let me go through another problem with silicon that has been solved. It's the fact that silicon has no electro-optic effect. And the electro-optic effect is needed because what you want to do is that you want to code your electrical signal into optical signal. And therefore, so you need to be able to have a change in the optical transmitted beam that depends on the electrical bit that you want to transmit. And so there are several techniques in order to do that. So the first one is based on thermo-optic modulators, which is a technique that is very cheap and easy to fabricate, and this is one of the techniques that we are also using a lot. And so what you have here is that you have your silicon waveguide, a very small core silicon waveguide where the light is traveling through. And then you have the silicon oxide cladding, and you can notice the numbers here. Okay, so the silicon waveguide is 500 nanometer wide and 200 nanometer thick. And then on top of the silicon core, so we have a silicon oxide cladding, and typically the thickness of this cladding is 800, 600, 1 micron. So it's thick. And then what you do is that you deposit on top of the silicon oxide a metal wire. And And the reason why you deposit the metal wire is because now, if you let the current going through the metal wire, you have that the wire, due to the Joule effect, heats up. And so you increase the temperature of the metal, you increase the heat, and therefore, so what you have is that you have a flow of heat that from the metal wire flow through the silicon. And once the heat reaches the silicon, you have that the silicon temperature increase. And so if the silicon temperature increase through the thermo-optic effect, you have that the refractive index of silicon increases. And this increase in the refractive index is very localized where the metal wire has been deposited. And so now, if we look at the optical beam that is traveling through the silicon waveguide, it happens that when the beam is going through the region where you have the metal wire, it feels a different temperature, meaning that it feels a different refractive index. And therefore, what you have is that the phase of the light, while it's moving through this piece of waveguide that has a given length L, so the phase of the waveguide is changed. And the rate of change of the phase of the waveguide depends on the increase of the temperature of the silicon. And the increase of the temperature of the silicon is essentially dependent on the current that you are flowing. And therefore, what happens is the fact that if you do not have any current here, you do not have any increase in the silicon temperature. Therefore, you do not have any additional phase shift that is suffered by or experienced by the optical signal that is propagating here. On the other hand, if you increase the current here, you increase the temperature, you increase the refractive index, and therefore you increase the phase of the light. And so in this way, we have a tool to change the phase of the light that is propagating in that waveguide. And now if we put this piece, this component, which is called a thermal phase shifter, into a Mach-Zehnder interferometer, so now we can control the constructive or destructive interference out of the Mach-Zehnder. And so the idea is very simple. In Mach-Zehnder interferometer, what you have is that you have your waveguide, and then you split the waveguide into half. So one part of the optical signal is going in this arm here, the other part is going in that arm there. And then here you have that the two beams recombine. So here you have a combiner. And so the result of the interference between the light that is going through this arm and the light that is going through that other arms determine whether you have a signal here or not. And so the intensity of the light that is coming out from this waveguide here depends on the phase difference between the light that is moving in this arm and the light that is moving in that other arm. But the phase here is controlled by the current. And therefore, by using this interferometer, you can modulate the optical intensity out of the Mach-Zehnder interferometer by modulating the current that is going through. And so here you have an optical modulator. And therefore, in this way, you can encode in the intensity of the light beam your electrical information. So this is very effective. It costs nothing because it's a piece of metal on top of the silicon, but there is a problem. So the switching time is the switching time is long, few microseconds. Why so long? Because you have to heat up the silicon, and then you have the inertia. So once the temperature of the silicon has increased, so this heat should flow away in order to get back to the initial condition. And therefore, so the typical frequency that you can encode your signal into this Mach-Zehnder are in the order of the megahertz, which is low for optical transmission. And therefore, people start to think about what can we do. And so the solution was to use what silicon is good at, meaning that silicon is a semiconductor, is very good at transporting free carriers. And therefore, people have developed modulator by using what is called the free carrier or the Drude effect. So by these terms, what we are meaning is the fact that now the increase in the free carrier concentration, so those are electrons, or in the free hole concentration, those are holes, impact in a change of the refractive index of the material. And therefore, what we can do is that we can control the refractive index of the material by controlling the injection or the depletion of a PIN junction. Okay? So this is very simple, and this is indeed what happens. And so therefore, here you have two different possibilities in order to make this optical modulator by using this carrier, this Drude effect. So the first one is to build a PIN junction. So you have this waveguide. Here you have a p-doped side of the waveguide. Here you have the n-type doped side of the waveguide. And then by applied a forward bias, you have injection. And so you change the carrier density in the region where your optical mode is propagating. By changing the carrier density, you change the refractive index. And therefore, you can make a phase shifter. You change the phase of the light. And so you make a phase shifter. And now you integrated this stage here, this phase shifter, into a Mach-Zehnder modulator, and then you can modulate Mach-Zehnder interferometer, and then you can modulate your light. Quite easy, no? Or, on the other effect, what you can use is a carrier depletion mechanism. So in this case, what you do is that you apply a reverse bias to your PN junction. And so in this way, you deplete, so you void the waveguide by carriers. And so by changing the free carrier concentration in this region, you change the refractive index. And therefore, you make a phase shifter. And therefore, you can make a Mach-Zehnder, use this phase shifter in one arm of a Mach-Zehnder interferometer, and therefore, you can make a modulator. And this is quite effective because you can use, by using this carrier depletion effect, you can go up to some 30 gigahertz in modulation frequency, even larger than that. And indeed, so people have demonstrated by using this kind of principle, they have demonstrated Mach-Zehnder interferometer. You see here is the paper by Delphine Maris-Maury, also in Paris, that have demonstrated in 2008 a very good Mach-Zehnder interferometer. Sorry, a very good optical modulator. So what is the problem with this kind of approach? So this approach is very effective, but the problem of this approach is the fact that the refractive index change with respect to the thermo-optic effect that I was discussing before. So the refractive index change is very small. And therefore, what you need to have a very long Mach-Zehnder interferometer in order to get a very good extinction ratio. So this is one caveat of the approach. But nowadays, so you can get those electro-optic modulator integrated in silicon quite effectively. And then the last problem with silicon I have already discussed is the fact that you cannot make a laser by using silicon, and therefore, so the only solution left is to use 3-5 semiconductor in order to make the laser in silicon. But then you need to make those 3-5 semiconductor on the silicon platform. And so here there are several approaches. So the first one is what is called the flip chip bonded approach. So what you do is that you take a laser, a 3-5 semiconductor laser, and then you bond this 3-5 semiconductor laser on top of the silicon. And this is working. Here is an example of this device where you have the silicon die. Here you have the 3-5 semiconductor laser device, and here you have the optical fiber. And what you immediately recognize here is the fact that the fiber are enormous. The silicon, the 3-5 die is enormous with respect to the small size of the silicon anyway. So this is working. The only problem is the fact that this is an approach that is costly because you need to have a machine that take your die and that place your laser and that place your laser on the silicon. And so you can do that, but only for few lasers. So if you want to integrate more lasers, so you have to change the approach. And so here is an example of one of these optical cables that are fabricated by using this approach. And so the other option is to use what is called the heterogeneously integration of 3,5 on top of silicon. So you cannot grow directly 3,5 on silicon because of the lattice mismatch. Okay? This is the first problem. The second problem is the diffusion. The gallium and arsenic, the indium and phosphor diffusion into the silicon. So you know that in silicon, phosphor is a dopant, but if you make an interface between indium phosphide and silicon at high temperature, so you get that the interface blur. So you have a diffusion of phosphor from indium phosphide into silicon, which change the properties of silicon as well as destroy your indium phosphide wafer. And so the direct heteroepitaxy of 3,5 on top of silicon is not possible. And therefore, so the idea is to use what is called a heterogeneous integration. And by this, what is meant is the fact that you take a piece of so what is meant is that you take a piece of 3,5 and then you bond this piece of 3,5 on silicon. So the process is the following one. So you take your waveguide in silicon, you do your processing, and here is the example of your waveguide. And then on the other side, you process your 3,5 wafers, your 3,5 die, in order to make, for example, multi-quantum wells, so the active structure of your laser. And then what you do is that you expose, you functionalize, you activate the surfaces of silicon as well as the one of a 3,5 semiconductor. And you do that, for example, by exposing to an oxygen plasma or by depositing on top of the two some specific polymer. And then what you do, you press the two together, you bond the two together by doing a low temperature process in such a way that now, so you have chemical reaction that happens, bonding chemical reaction, because the surface is very reactive because it's been exposed to an oxygen plasma. So this surface here and that surface there, both the surfaces are very reactive. And therefore, in this way, so you can get a very stable, very sticky interface between the two. And so once we have done that, so then you can do the usual 3,5 processing. So here is the scheme. So you start with your SOI wafer, you planarize, you bond, and then you remove the substrate of 3,5 semiconductor, and then you process the 3,5 semiconductor in order to make the laser. And the outcome is quite successful. Here is an example of one of those. This process, this image is coming from Leti, which is a silicon foundry in France, in Grenoble in France. And where you see here are all the pieces of 3,5 semiconductor that have been bonded indeed on top of the silicon. And then you can make the kind of laser that you want. Here is an example of a process of a microdisc indium phosphide laser that is indeed very well working. And this is also in 2018. And here is another approach that is the approach followed by the Americans in Intel. And this approach here is the fact that the silicon is used also to make an optical cavity. So they call this an evanescent silicon laser. And so the devices are quite well, so they are quite working. And here is an example of the kind of transceiver that Intel is fabricating by using this heterogeneous integration. So they are able to put into a fully microelectronic process for laser, and then the 4 modulators, then the multiplexer, and couple everything with the fiber. So this is the transmitter chip. And this is actually something that is sold, I guess. So they are actually selling those transceiver, 800 gigabit per second. So, and they are able to demonstrate up to 1.6 terabit of data per channel. And this was one of the press release by Intel VPs, where he was comparing. So the reason was to try to convince people that these active optical cables, so cables where you have optical fiber and then on the end of the fiber you have a transceiver made by silicon photonics, that cable are actually important for data centers. And so what she was demonstrating here, a comparison between a standard copper cable and this active optical cable enabled by silicon photonics. And what you see here is the fact from, on one side, the bandwidth, so the capacity. For the copper cable, you have 120 gigabit per second, while for the silicon photonics cable, you have 1.6 terabit per second. So you see the difference in capacity. But then you have other advantages. Any guess? What's other advantage here? Sorry? Perfect. Very good point. So you see how. So the copper cable, how it's bent. And you see the silicon cable, how it is bent. So you can bend more the silicon cable because it's lighter. And then the second big advantage is the weight. So the silicon cable is essentially glass. So it's very light. The copper cable is very heavy. And so you have many different advantages moving from copper to silicon photonics. Anyway, so they try to make, so they are selling millions of those transceivers nowadays. And so here is the hand. And what you see is the fact that in silicon photonics, people have exploited essentially all the advantages and they have overcome all the disadvantages of silicon. And indeed, so nowadays what is happening is the fact that the optics is moving more and more towards the heart of where data are processed. And this motion from the long-distance communication up to the intra-chip communication by using light is motivated by the fact that there are huge market opportunity, because once you start to send billions of optical of silicon photonics components, so then there is really a huge market. But the problem is not only the market, is also the fact that nowadays people has to transfer a huge amount of data, and therefore with silicon photonics you can do that. By using copper you cannot. And so this is the kind of timeline that silicon photonics has followed in the past. So I started by saying that during the 90s we demonstrated together with other the proof of principle working of the device from 2010. So we were able to demonstrate heavy integration, and nowadays, so we are really in the booming of silicon photonics. So here is a typical. This is slide are coming from the Photonics Research Group in Ghent, which is one of the most important groups working on silicon photonics in Europe. And in this device, you see the typical silicon photonics chip that you are using. And so what you have here, you have different functionalities. And what I want to show you now is the fact that all those different functionalities are indeed available in. Be able to make very low losses waveguide. So the answer is yes. And this is the typical size of one of these waveguide. So in silicon, so those are numbers that you need to know by heart. So in silicon, you have the refractive index of silicon is 3.45, and the refractive index of the cladding is 1.45. Then you have the waveguides are extremely small. So you have waveguides that are 220 nanometer thick. So this is quite a standard. 220 nanometer thick and 450 nanometer wide. And you use these numbers because you want to have a monomode waveguide. And these large index contrasts allow you to have a very sharp bands, 2 to 3 microns. So when we are talking about the size of the components. So always we are talking about components that have a size of few microns. And then the numbers here are a number where you can use silicon or silicon nitride, and the typical propagation losses that we get are in the order of few dB per centimeter. With silicon nitride, those numbers are quite old because nowadays silicon nitride, so they are able to make optical waveguide with losses that are measured in dB per meter. No, this is number, yeah. dB per meter, okay? Silicon, dB per centimeter, silicon nitride, dB per meter, okay? So it's a huge difference. It's a factor of 100 of difference. And this is the reason why in quantum photonics, where each single photon counts, people are trying to use silicon nitride. Because you lose a very small number of photons by using silicon nitride, okay? So then the modulator, I have already shown you that you can do modulator with a very high frequency. Yes?
Sir, you just mentioned about the losses what we have in silicon waveguides. So what is the main origin of that loss? Is it the sidewall roughness, or is it the free carrier absorption loss, or?
Is the first. Is the wall roughness. So this is the main source of loss. While for silicon nitride, the main source of loss is not the sidewall roughness, but the residual contaminants in the wafers. Sidewall losses scale with the refractive index contrast. Okay, the larger is the refractive index, the more scattering you get out of the waveguide. So if you have a roughness of a few nanometer with silicon, since you have this kind of index contrast, you have a huge scattering loss. But silicon nitride, you have the same nanometer size, but since the refractive index of silicon nitride is 2, you have a much reduced scattering from silicon nitride. And this is the reason why, by using the same process, which means by using the same lithography process, you can get a much better propagation losses for silicon nitride than for silicon. So modulator, I already told you the way to use this modulator, so you can go up to 100 gigabit per second by using this depletion modulator. So then we can integrate photodetector, which are quite good, very efficient, so they can work at very high frequency. We can use an integrated laser, so there are these approaches that I have already discussed. If you want to integrate only a few of those lasers, so flip chip integration is a viable solution, even though you have a very difficult alignment process, so this is very labor-intensive way. Otherwise, you can make wafer bonding, or what is actually nowadays used in most of the silicon foundry is the approach that is called microtransfer printing. So it's a very simple process by which you have a stamp, an elastomer stamp, onto which you attach small, what they call coupons, a small piece of a 3-5 die, and then by simply printing those, by using this stamp, by printing the silicon wafer, so you transfer the coupon onto silicon. So this is the way they are using, okay? Then I show you that it is possible to integrate silicon with electronics. Here is an example of one of our chip. And what you see here is all these white lines are metal lines that are on the silicon circuitry. And all these metal lines are used to locally inject current, whether you have a PN junction or whether you have there a thermo-optic, or you want to use thermo-optic effect. And then, for example, here you see that you see a black rectangle. The idea of this black rectangle is due to the fact that there, in order to confine, so there you have a thermal phase shifter, and in order to confine the heat, what you do is that you dig some trenches into the silicon. So you make these trenches in order to thermally isolate the waveguide from the nearby silicon. And so that you have to heat only a very small piece of silicon. And so you have a very localized heating, meaning that you do not have a thermal crosstalk, meaning that you want to change the temperature here, but since the heat is flowing, so you have a change of temperature also there. So you have a thermal crosstalk. But by using the trenches, you localize the heat here. Okay? And so you obtain the double advantages. So the first one is that you reduce the thermal crosstalk, as well as you increase the frequency of your phase shifter. And then what you see here is all the pads on top of which we do bond metal wires. Okay? And so what you have a wire bonding machine that contact all those pads. And so in this way you can interface your chip with a typical holder. Here is one of the chips that we are working. So this is actually a neural network. So this is a platform for artificial intelligence. And you see here all the metals gold wires that are used to drive the current into the chip. So then you can interface quite easily the fibers by using this either what is called the back coupling technique, by which you use inverted taper. So you place your fiber on the sides. So here you have the edge of your wafers, and then you use the fiber and to inject the light there. Or you can use the grating approach, where you inject the light from the top of the wafers. So this is the typical testing that we have in the lab for back coupling approaches. So here we have nano positioner, so piezoelectric control stages. And the reason is because we need to couple the optical fiber into a 400 nanometer wide waveguide, and so the alignment is very crucial. And so in this case it's called a back coupling, because you couple the light from the edge of the chip. Or what you have is much simpler way to use grating coupler. And so in this case the circuit is here, and the fiber is coming from the top, the fiber is coming from the top. And so in this way, so you can couple the light very easily. But what is even more important, the fact that you can use those grating coupler, is the fact that it allows you to make wafer level testing. So you can test the behavior of your devices before dyeing the circuit, before isolated the single photonic dyes. So this is a full wafer. And here you have the fibers that are automatically placed like in a standard microelectronic testing machine. So everything is done automatic at the wafer level process. So then all the silicon photonics building blocks are available. And so today, so where are we with silicon photonics? We are at the stage where we have heavily integrated and fully connected electronic chip. Here you see an example of one of these photonic chip in a package. So here you see the PCB, the board, the electronic board. And then on top of the electronic board, you have this big square here that is the silicon photonics circuit. Here you have the optical fibers that take the light from outside into the circuit, or take the light from the circuit and send the light outside. And here you see a microelectronics circuitry that has been flip chip bonded to the silicon photonics. So where are we now? So we are in the stage of being able to demonstrate heavily integrated devices. And nowadays, having millions of different components in silicon photonics integrated is no longer an issue. So you can have a few thousand, few millions of photonic component integrated in silicon. You have a full package system, and even so you can do, and I will tell you something about that tomorrow. So even you can make a very complicated system that are based on silicon photonics. So this is a system that we have developed in order to test the presence of contaminant in milk. And what you see here is the tank where the milk is placed. All the chemicals are placed there. So you have all the pump. And the silicon photonics circuitry here inside is a very small piece of silicon that is placed in this part here. So let's coming to the conclusion of this part. So the platform is a quite stable platform, which is this silicon photonics. So the applications are many different. So you have application in optical communication, so you can buy transceiver based on silicon photonics. You have application in life science. You have system that can perform biosensing, so lab-on-chip application. So you have application in healthcare. There is a company that is called L03 Photonics that is selling a silicon photonics sensor for the smartwatches. You have application in the automotive field for LiDAR application. So light. You have application of silicon photonics in data center, in photonic computing, in quantum computing. So the amount of market, the amount of money that silicon photonic is making is enormous. You see here is the forecast that in the next year, so the aggregating increase of the market will be about 44%, and most of the increase of the market is in datacom because to allow artificial intelligence developing, and in optical computing. So those are forecast, but looks quite reasonable. And indeed, just last few weeks, NVIDIA has announced that they are implementing silicon photonics into their system, and the idea is to use silicon photonics in order to make switches for the on-chip network. And the approach is what is called co-packaged optics, meaning that at the same time you package together the electronics and the photonics. So in this co-packaged optics approach, you no longer have optical fibers. So you only have silicon photonics circuitry in order to handle all the transmission of data on these very high and fast GPUs. So what is the future here? And so this is one graph, but there are many others by IBM that is showing the way they are considering in order to increase the system performance as a function of the year. So this is what is by only considering the scaling of CMOS, so what is going to be the increase of the performances. And here instead is the increase of performances when you change the paradigm based on the way you do the computation. And so where are the two most important and two most impactful development that should occur now? One is neuromorphic computing, meaning computation inspired by the brain. I already said several times, but I will talk a little bit about that. And then the second one is quantum computing. So therefore, the future are those two lines. So neuromorphic computing and quantum computing. Still, in quantum computing, so there are several. So this is the arrays where several approaches are trying to place a key role. So here you have platforms that are based on superconducting transmon, IBM, Google. So here is a platform that are based on ions, atoms. And here you have the platform that is based on photonics and silicon photonics, clearly. And still, so there is no answer. So all those platforms are actually actively pursued. And so what I think is that the future is quantum and brain-inspired. Quantum because of quantum photonics, brain because of neuromorphic photonics. So now I think it's time to stop here this brief. You saw? I say brief introduction, indeed, it's 2-hour-long introduction. And if you are interested, so these are a few references, books about silicon photonics that I edited. And clearly what I need to do, and I always acknowledge the people that are working in my group together with me in order to make our activity successful, and the different funding agencies. Okay, I think that for now I can stop here. And if you have any question, I'm happy to take any question. Yes?
So how the concentrations of electron and holes is affecting the optical properties?
So there is this very famous formula, which is called the Sorev formula, now I give you, which is the one that all the people are using in order to so this is a formula that gives you quantitative the change in the refractive index depending on the injection of electrons and depending on the injection of holes. Okay? And therefore, by using this formula, you know a p-n junction, so you know the injection, and you can estimate the refractive index. And once you know the change in the refractive index, then you put everything inside a Mach-Zehnder interferometer. You can use this configuration, which is a quite simple one, or you can use a push and pull configuration where you have two phase shifters here, which are operated at different voltages. Okay? And therefore, now you can modulate the light here by controlling the phase shift between the light that is going through this arm here and that arm there. And since the refractive index change is small, what you have is that the Mach-Zehnder need to be very long in order to get a good extinction ratio.
The size will increase then. If you are using long Mach-Zehnder, the size will increase.
Yeah, so this is indeed a problem. This is indeed a problem. So this is the reason why people are using Mach-Zehnder is because those Mach-Zehnder are essentially have a broadband response. So you can decrease the size by using micro-ring resonator. But micro-ring resonator are resonant devices, meaning that the response is very narrow. So only for that specific wavelength, the micro-ring resonator is able to modulate. If you change the wavelength, so you are in trouble.
The NVIDIA switch, what they have announced. So what is the technology what they are using inside that? Any idea?
Silicon photonics, and then they do not say details clearly. NVIDIA is never saying details. Other question? Yes, here.
Said that you are talking about that 220 nanometer technology. So whatever your university is having the fabrication facility, so those are working on 220 nanometer, or is there any other availability there?
No, there are other availability. Okay, so the 220 is because people want to have a standard, because this is the thickness of the device layer in the SOI wafer that you So typically the process occurs in this way. So you buy the wafer, the SOI wafer, and then you process the device. And so depending on the thickness that you decide, you buy the specific wafer that you are interested in. And so 220 is typically what you consider for a single etch process, meaning that you have only one etching depth. But then you can have a double etching process. Typically, gratings are done by using a double etching process in order to increase the efficiency of the grating or reduce the coupling loss. And in that case, so you can start from another silicon thickness. And then, if you now are willing to work no longer in the C band, but you want to work in the visible by using silicon nitride, for example, so then the thickness is again different. So the thickness depends on where you want to work. But for silicon photonics, the standard is 220 nanometer because less cheap, less expensive SOI wafers. Okay. Okay, so it's lunchtime, I guess. Okay.